one of the most critical aspects beyond this is safety. And with that, our final speaker in this session, Dr. Darren Tan, CEO of UNIGRID Battery, will shed light on the safety properties of advanced sodium-ion batteries and present data on their thermal stability. So please join me in welcoming Dr. Darren Tan to the stage.
So my name is Darren. I'm the CEO and co-founder of UNIGRID Battery. UNIGRID, we are making advanced sodium-ion batteries for both clean mobility and storage applications. I'm happy to go last in this session. So the previous speakers have gave excellent background on sodium-ion batteries and some of the cutting-edge technologies that are being worked on. So in the last few minutes, I've been removing a lot of background slides because we are running behind time. So hopefully this will be a lot more concise. So at UNIGRID, we really want to solve one problem, which is safety. All of us, we love our batteries, we love our devices, we love electric cars, and we want the ability to store and use renewable energy whenever we want. But the biggest problem we have today with batteries is still safety, because they all have a small but probable chance of blowing up if the right conditions come up. And the world has already enough fires and natural disasters. We don't need any more of it. So we do need better solutions. These are some of the recent incidents that happened in North America this year, and some of the big nasty ones also happened very close to us in South California. So as such, UNIGRID's focus is to develop a sodium-ion battery that is not only equivalent to lithium-ion in performance, but the exception that it cannot undergo thermal runaway. In other words, we want to make a battery that eliminates battery fire hazard risk entirely, not just lower this risk. So here is a third-party safety test of cell abuse scenario between lithium-ion and a commercial sodium-ion that you can buy online, as well as UNIGRID's sodium-ions. So they're all 18650, same form factor. You see that lithium-ion, under the fully charged state, it bursts into flames once the nail gets in. The commercial sodium-ion also releases a lot of heat and fumes, but the sodium-ion built by UNIGRID there's no fumes or flames at all, so it's a lot safer. However, personally, we don't like nail penetration tests. We believe they are very unreliable, and they often don't offer an effective way to quantify safety metrics. We need a better way to measure safety and therefore guide us in designing safer batteries. So instead, we propose ARC testing, or accelerated rate calorimetry, as the better standard for safety comparison. The ARC test basically measures the temperature response of a battery when it's being heated from 500 to 400 degrees Celsius, or 750 Fahrenheit for my North American friends. And they have standard parameters to follow, so everybody uses the same kind of conditions to test. So this will allow us to see the full battery at the charge state in its naked form, and we can know exactly what will happen and when that thermal event occurs. To use layman terms, our test is kind of like a battery barbecue test. And I got ChatGPT to generate this image for me when I type in battery barbecue. So that's a fun thing they spit out. I'll share snippets of it in this session, but we published the full test write-up and summary on our website. If you're interested, you can go and take a look. We included reference data for NMC, LFP, and also NFM. So I will just talk about two examples here because we have limited time. The first is an ARC test result of a generic NFM sodium-ion battery. So the test starts at about 50 degrees. It gradually heats the battery up, and nothing really happens as it heats up. Only at about 130 degrees, that's where the cell starts to short, and you see the voltage drops to 0. But still, nothing really happens. So cell shorting does not cause thermal runaway. The temperature of the chamber keeps going up, and only past 200 to 250 degrees, that's where we see a spike in thermal profile. So this is indicative of thermal runaway happening. And a second plot that we really want to pay attention to is this temperature rise rate versus temperature plot. You can see that initially the temperature rise rate also remains quite low, but during thermal runaway, it kind of zooms up really fast to hit a maximum rate of about 100 degrees a minute. That's really hot, really fast, faster than you can microwave your frozen meal. So as a result, the cell gets